Okay. Yeah, thank you, Raul. Hi, good morning or good afternoon, everyone. I'm happy to see that it's probably most of the people are here. So it's good. If anyone has any quick comments or questions from yesterday, um, this might be a good time before I continue with the topics of today. I don't know if anyone has some pressing questions we can address now. Otherwise, we can just begin with continue with the topics. And remember, if at any point you have a question, you feel free to unmute yourself and, you can always ask politely for, and then I can pause for a second and, and try to answer the question. Okay. So yesterday we left off with some isospin calculations for the scattering processes. Um, So I just wanted to, um, yeah. So that was yesterday. But before we talked about hadron physics and the isospin symmetries and flavor symmetries. We left off with classical field theory. Let me just draw very quickly this table that I had yesterday about classical mechanics and versus quantum. And then the degrees of freedom might be finite or infinite. So here you have something like X and P. In quantum mechanics, you have momentum and a position operator and some states, which is what describes the particle, these vectors in a Hilbert space. Then in classical mechanics, you can have a field theory with an infinite amount of degrees of freedom. And we will see that in quantum, the quantum version of this in quantum field theory, you have operators that depend on a space-time variable. They have their conjugate momenta, and then there's still states that describe, if you wish, the different configurations that the system can take. Okay, so we're gonna begin by talking about the Hamiltonian formalism of um, classical mechanics, and then we're gonna see and then we're gonna use that for our quantum field theory version. So the Hamiltonian formulation is an alternative, but equivalent to the Euler-Lagrange equations. So this is equivalent to the Euler-Lagrange equations to solve for the time evolution of a system. And it begins by defining some conjugate momenta. Which we're going to use symbol pi, those some index A in case there's multiple fields. And it's going to be based on our Lagrangian. And it's going to be the derivative of the Lagrangian with respect to the time derivative of each of the fields appearing in the Lagrangian. This is what's going to define our conjugate momenta. And so the Hamiltonian is basically going to be equal to this conjugate momenta times the derivative with respect to time of each of the fields. So you have the index A being contracted here to sum over all the fields minus the Lagrangian. And then you substitute each of the instances of pi A, so that only pi a appears instead of whatever this value is. So let me do a quick example for our scalar field theory that we saw yesterday. So we have this scalar field theory with a very simple Lagrangian that's quadratic in the fields. You can calculate the conjugate momenta, and in this case, you're going to find that it's the derivative with respect to time of the field. With that, you can calculate your Hamiltonian, which is going to be pi times the derivative with respect to time of the field, which this on its own, it's pi. This is capital pi minus the Lagrangian. And then we're going to substitute this so that we have only terms that depend on pi, and we don't have any terms that depend on the derivative with respect to time of the field. So what we're going to get is 1/2 pi squared plus the gradient of our field, gradient of our field squared plus the mass term, right? And something that you can notice if you compare this to the classic formulation of the Lagrangian, where you have kinetic energy minus potential energy, or the Hamiltonian, where you have kinetic energy plus potential energy, is that this term, so the potential energy over here, can be identified with this part of the Lagrangian, whereas the kinetic energy, it's only the time derivative piece. So time derivative because we have identified this time derivative here. And that's going to be useful to remember in the sense that the interactions in our theories are normally going to appear in B, in the potential part. So this is the potential part of the theory. Meaning that if we have some Hamiltonian of an interacting part of the Hamiltonian, we can quickly identify it by looking at the interacting part of the Lagrangian and adding a negative sign, right? Because there's a negative here and then it's positive over here. So there's an easy identification of the interacting parts of the Hamiltonian by looking at the Lagrangian. Okay, so that's basically all that we need to know about classical Hamiltonian mechanics in classical field theory for now. So let's name these sections. This is gonna be A, we're gonna do B, and then we're gonna go C. So this was A, let's see. So nothing too complicated here. Now let's do B. So quantum mechanics. Quantum mechanics, for this, I'm just gonna use the harmonic oscillator as an example, and you'll see that everything that we're gonna use here is gonna be useful for our free scalar theory. We have the harmonic oscillator, and what we do is we have position and momentum, and we quantize them, meaning we promote them to operators that satisfy the commutation, certain commutation relations. So the most important one is that the momentum and the position do not commute, and different directions, except unless there are different directions, but if it's the same direction of position, the same direction of momentum, they're not going to commute, and the commutator is going to be given by this formula. So note that I'm using units where h bar is equal to 1. So that's the commutation relation. Um, or the position itself, it's gonna commute, and the momentum with itself, it's gonna commute. So in the harmonic oscillator, the Hamiltonian is given by the momentum squared plus a potential that is squared in the position, right? So we can do, and if we make this quantum, that just means promoting everything to an operator in a Hilbert space. There's a nice trick where you can replace the position or change the basis, if you wish, uh, to another set of operators called A and A dagger. So you can propose this alternative for the position, and you will find that if you want to reproduce the commutation relation, then the momentum is going to be given by this other operator. And now your Hamiltonian is going to be, in a sense, diagonalized in this basis, since now you have only one operator here. So eigenstates of this operator, so it's one operator. Eigenstates of this operator are going to be our energy states. And typically what you want with a quantum theory is to find the spectrum and then calculate matrix elements of that spectrum. So as soon as we find the eigenstates of this operator, then we're pretty much done with the harmonic oscillator. So you probably are familiar with the solution of this. We propose some energy states n. So we define some energy states n. We said that their energy is given by En, and then we can use the fact that there's going to be a commutation relation between H and a dagger, which is going to be given by W a dagger, and something similar with HA. And in that sense, we're going to find that, for example, HA acting on the state n, we're using the commutation relation. It's going to be given by En minus omega an. So this state is still an eigenstate of the Hamiltonian. A is lowering the energy of n. So that's why it's called the lowering operator. And you can do a similar calculation with the raising or with the dagger operator to find that it increases the energy of the state. So a dagger is the raising operator. Fair enough. And then you can think about what's going to happen if you keep applying this A operator to a state. If you apply it multiple times, you're going to continue lowering the energy of your system. And you can propose that, okay, there has to be a lowest energy state, your ground state, that is going to be annihilated by the lowering operator. So there has to be some bound from below of the Hamiltonian energy. And once you hit that state with your lowering operator, you should annihilate it. You can you can easily calculate the energy of this state to be omega over 2. from our Hamiltonian. And from there, uh, you can find that if we define states n to be the raising operator applied n times on the ground state, then the energy of these states is going to be given by n plus 1/2 omega. Okay, so nothing too crazy. We have diagonalized this theory. We have found the spectrum. We have found the energy of each of the states. And before we move on, I just want to introduce another operator, which technically it's already there. And we're gonna call so this operator, which is very simple, it's gonna be called the number operator. And if you see the Hamiltonian is given basically by omega, the number operator, plus 1/2, meaning that if I apply the number operator to a state, I just get the n back. So that allows us to count the number of quanta that we have in a given state in our system. So, so good and nice, but this is just a finite amount of degrees of freedom. Let's go and look at something more interesting, which is C, part C. This is going to be actual quantum field theory. So again, we just take our fields, so phi of x, and in the Hamiltonian formalism, this conjugate momenta pi of x. Just a quick note, this field is called the conjugate momenta in the sense of the Hamiltonian formalism. That has nothing to do with physical momenta or scattering momenta. This is just the conjugate momenta with respect to the Hamiltonian transformation. Okay. And we're going to promote them to operators that satisfy the commutation relations that we said before. So again, just for the sake of the argument, we're going to have multiple fields with the multiple conjugate momentum. So each of these operators, so I'm not going to put the hat each time. So for now, you have to remember that now these are operators in this quantum field theory. You will have that different operators at different locations in space-time. And these are going to be given, the commutation relation is going to be I, but then you have to make sure that the two of them are sitting on top of each other. You have a Dirac delta x minus y, and you have to make sure they correspond to the same species of field. So a Kronecker delta AB. Again, the fields with themselves, they commute. And the momenta with itself, it commutes. And these are known as the equal time commutation relations. So something to notice about the Hamiltonian formulation is that we're picking a preferred time direction. In principle, if you have Lorentz invariance, you might imagine that any time direction, and when I say time direction, I mean time axis related by different Lorentz boosts. If you perform a Lorentz boost, then your time gets a little bit contracted, and then technically you have a different time axis. But in the Hamiltonian formulation, you pick a specific time, a specific frame, You impose equal time commutation relations, meaning there's a frame where these commutations apply, but then if you boost to a different frame, then the commutations will apply to times to fields at different times. So we're picking some special frame in a sense. And you might worry that this will break Lorentz invariance in some sense, but happily this doesn't break Lorentz invariance. As we will see later, you will recover states that have that satisfy the dispersion relation of relativity. And that's because the Hamiltonian formulation is equivalent to the Lagrangian formulation, which is Lorentz invariance explicitly. Okay, and now how do you do quantum mechanics here? Well, you do the same thing as usual. You have to solve the Schrödinger equation for your states by hopefully diagonalizing the Hamiltonian. So the Hamiltonian here is equal to the spatial integral of this h that I was talking about before. So technically this h, so h in the case of the free field theory was 1/2 of pi squared plus 1/2 of the gradient of the field squared plus 1/2 of the mass squared of the field squared. This is technically the Hamiltonian density. Um, and then when you integrate it over the volume, then you get the full Hamiltonian h. And this is what goes into your Schrödinger equation. And this is the operator that you have to actually diagonalize to obtain the spectrum of your theory. Okay, so if we use this specific Hamiltonian, then you still have quadratic dependence on your fields. And as you might imagine, we can use a similar trick to what we did with the harmonic oscillator, where we just say that the fields at a given space-time point, at a given space point, so we're still in fixed time, are gonna be some Fourier transform. So the factors here are gonna be conventional, but very similar to the factors in the harmonic oscillator case. Oh. Since this is basically is the extension of the harmonic oscillator to an infinite dimensional system. Okay, so let me just look at the harmonic oscillator for a second. So this is what I'm saying is the new decomposition of the fields. And this is what I had. Oh, sorry. So this is what I had earlier. See if I don't mess it up again. This is what I have now. So it's the same decomposition modulo the Fourier transformation because now we have an infinite dimensional number of degrees of freedom. So we don't have a single position x, but we have an infinite amount of labels in our field. So we have this Fourier transformation, but then we have the same structure of the summation of the two raising and lowering operators. And then you might wonder, what is this 1 over square root of 2 omega p? So here in the case of the harmonic oscillator, this omega was coming from the potential part of the Hamiltonian. And similarly here, when we do the Fourier transformation, so let me erase this. So when you do a Fourier transformation of the potential part of the Hamiltonian, you will get something that goes like p square substitutes the gradient becomes p squared, and then you still get the m squared of the field. This is, the Fourier transform is a factor of px. So this omega p is going to be equal to this p squared plus m squared. Okay? And if I propose that for the field, then my conjugate momentum is going to be given by a very similar integral to what we had in the case of the harmonic oscillator. So you have a factor of minus I. The potential energy part came up in the numerator. And now you had, remember these are space-time, space P and space X here, multiplications, dot products. Okay. You can do this transformation of the fields, propose this Fourier decomposition, and you will find that these new operators, again, satisfy a relatively simple commutation relation based on the commutation relation of the fields and the conjugate momentum. So now these guys will satisfy 2 pi cube and the three-dimensional Dirac delta p minus q. So look carefully that these guys depend on the integration of the Fourier momenta p. And they satisfy this commutation relation. The lowering operator with itself commutes, even for other momenta, and same for the raising operator. Okay. So nothing too crazy here. Now, the Hamiltonian, again, is going to be diagonalized when we write it in terms of these operators. So you can, substitute these two guys into the Hamiltonian that I gave you before. And what you will find is that we get this three-dimensional integral, omega p, ap, dagger ap, this dependent momentum, plus 1/2 of omega p 2 pi cube delta x minus x, which is 0. Yeah. So the first term, it's easy to interpret. So let me just think about the first term for a second. And if you remember, I defined earlier a numbering operator, which in this case depends on momentum. And it's going to be AP dagger, AP. So this counts the number of particles with a certain momentum and then multiplies them by the energy and then sums over all of those. So that's an easy term to understand. This is what you would naively expect for the energy of a free system. The second term is the energy of the 0 point. So if you remember in the Hamiltonian, in the harmonic oscillator, we have a non-zero energy for our ground state that appeared in the Hamiltonian. And this would be the equivalent here. However, if you notice carefully, this is basically a divergent term. So this is just going to be 2 pi cubed, 1/2 omega p, um, 0. Um, and the reason for this to be divergent should be at least expected in the sense that now we have an infinite amount of degrees of freedom. So if you sum all the energies of this infinite amount of ground states that you can have for each degree of freedom, you should expect an infinite amount of energy. You might think this could be problematic for the theory, but thankfully, what we are really interested on is differences in energies. So, calculating the value of the total energy of the system in quantum field theory is not going to be what we are actually interested on, but really on the differences in energies, so that we can ignore the second part of the Hamiltonian. And the procedure to do that, or the technical way to do it, to remove this infinity, is to define an operator called the normal ordering of the operator, where I'm using these dots to define that, where you place all the annihilation operators. So, for example, remember that this was defined as the integration over x, 1/2 of pi squared plus 1/2 of squared. So when we substitute for our raising and lowering operators, the normal ordering tells you put all a's to the right. And that way, um, and then you apply all the commutation relations to simplify it. So when you do that, the normal order Hamiltonian is just going to be equal to the first term. We don't get this infinite contribution anymore. So you might say, well, this is just a made up prescription, and in a sense it is, but it's also going to come in useful later on when we define what is called also time ordering. And there's going to be some relationships between normal ordering and time ordering of operators. Okay. So now to the states of our theory. Again, the Hamiltonian is now diagonalized in the basis of this operator. So we can easily find sorry, we can easily find the states and the spectrum of our theory. Again, you can find the commutation relation between the Hamiltonian and the raising operator to just be AP, and similar for the lowering operator. And we can define a state P. This is just a conventional definition to be 2 omega p AP 0. This is such that the internal the dot product, or the norm of the states, is going to be given by 2 omega p 2 pi cube. And as we will see, this is a Lorentz invariant quantity, or probably we will not derive that, but for now you will have to take my word for this. But this happens to be a Lorentz invariant quantity, so a normalization that's Lorentz invariant, and it's going to be by convention useful. So now the energy of our states that I just defined here, I'm gonna be just given by this omega p's. And now you might wonder, okay, so what about the momentum, the actual physical momenta? Can we calculate that physical momentum of the states? So that's something I didn't talk too much about before, but as I mentioned yesterday, your theory might have symmetries. So let me do a quick interlude about that.
Maybe Felipe,
Yes.
did you guys take a break at any point yesterday?
At some point, I stopped, asked for questions, had them, in a sense, had a break, but they were
Okay,
very short.
sounds good. Should we maybe see if there's maybe we
Yeah,
could
yeah, I guess this is a natural breaking point.
yeah, because these people have been really quiet, so I'm worried. I'm worried about the silence.
That's fair. Yeah, this is a good breaking point. If you have, if there's any questions so far, this is a good moment to ask.
Um, I wonder if we can do
I
like
have one question.
okay.
I don't know if I
Yeah,
understand when you said about the equal time commutation relation. Can you explain that again? Sorry.
yeah. So this has to do with how we're gonna quantize our theory, right? So so let me just step back real quick. In the case of the quantum mechanical simple harmonic oscillator system. So in that case, you only have a position and a momentum, and then when you promote them to operators, you never assume they have any time dependence. You just make them commute and impose these commutation relations. So in principle, there's something called the Schrödinger picture of quantum mechanics and the Heisenberg picture of quantum mechanics. And that's something that I'm gonna actually mention in a couple minutes. But the idea is that you can either have the states have time dependence or the operators have time dependence. So typically in quantum mechanics, we let the states have the time dependence, and so the operators are time independent. Now, in a classical field theory, your fields typically also depend on time. They are fields in space, but also fields in time. So in the classical field theory, you solve for the time evolution of your fields. So in order to have something in between, let's say, when you quantize your field theory, you have to first say, okay, let's make the operators time independent at first. So you pick some time, some initial boundary conditions, if you wish, and there you impose the commutation relations. And in a second, we'll see that you can make the time dependence of these operators explicit once you go into the Heisenberg picture. Then the commutation relations at a given time are still going to be given by the commutation relations here. But then at different times, then you will have some dynamics that will tell you what the commutation relations are. And they're gonna be a little bit more complicated. But you have to begin with some commutation relations for operators that do not depend on time. That's why we have to do these equal time commutation relations.
Okay, thank you.
I have a question. The infinite value when you are calculating the Hamiltonian, when I read that sometime, I read about that are related with ultraviolet divergences and the vacuum expected the expected value of the vacuum. Is that that it have some importance, something to do with that? I don't know.
So there's two terms contributing to a divergence here. So this term in here, this term is going to be proportional to the volume. So if you wish, this is just the fact that we have an infinite size universe, and then if we divide the Hamiltonian, the full Hamiltonian by this term, then we are looking at the Hamiltonian density. So this is a little bit more sensible quantity to calculate. What's the energy density of our field? But then if we still look at this other value, this is still an integral. This omega p at high values of p is basically becomes p. So you have a divergent integral for high values of p. And that's what's called an ultraviolet divergence. Some divergence that's coming from the high p region of our integral. The way to think about this, there's different ways to think about this, but one of the ways to interpret this is that our theory doesn't have to apply at all um, distances. So there might be a scale, some high energy scale where our theory breaks down and quantum gravity takes over, for example, and then this integral will have to have some cutoff, and then this becomes finite. Then talking about the vacuum expectation value, then that comes from a different place. The vacuum expectation value of a field, that comes from a slightly different place. Yeah, and then we will see that typically these ultraviolet divergences, or probably we will not see here, but in quantum field theory, these ultraviolet divergences are typically moved away or juggled around so that you get finite results. So similar to our case where we impose this normal ordering, we will see that, or typically in quantum field theory, you can get rid of ultraviolet divergences by imposing some physical constraints. So that's what normally happens.
Okay, thanks. Thanks a lot.
Hi, Felipe.
Hi, Ruben.
I have a question. When you say the Lagrangian is equivalent to the Hamiltonian, in
Yeah.
what sense?
Yeah, so I didn't derive this here, but something that you could do here after this, like once you have done, once you have calculated the Hamiltonian, you can go and calculate the time evolution of your system, right? And the time evolution of the system in the Hamiltonian formalism is going to be given by the time evolution of your operators. This is classical mechanics, okay? Time evolution of your operator is going to be given by the Poisson bracket of the Hamiltonian and your operator. And this Poisson bracket, sorry, the Hamiltonian, it's just defined to be some derivatives with respect to the fields themselves. So A G pi A G A. Okay. So you can use this Poisson bracket to look at the time evolution of each of your fields. And what you find is that the time evolution in this case is going to be the same time evolution that you find with the Euler-Lagrange equations. So in that sense, they are equivalent. Using the Hamiltonian formalism and the Poisson bracket, you have at the end the same time evolution and the same equations that if you use the Euler-Lagrange equations. in the quantum picture is going to be the same idea. If you use some Lorentz invariant way to calculate matrix elements or correlation or vacuum expectation values, it's going to be exactly the same as if you use the Hamiltonian formulation to calculate these vacuum expectation values.
Thank you.
Okay.
I would say maybe go on, but also let me encourage people. Like, if you have any questions, feel free to interrupt or put them on the chat. No need to be so shy.
Yes. Yeah. Thank you, Raul.
There, you get a question on the chat now. In the notes are said that there are other methods than normal ordering to deal with order ambiguity. Can you give an example?
Oof.
By Rafael.
Yeah. Um, yeah, I don't know something off the top of my mind that deals with this. One of the example in the notes is to rewrite the Hamiltonian in a different way. So if you haven't read the notes, I just write it here real quick. So the Hamiltonian for the harmonic oscillator was given earlier, but then you can always rewrite it as omega x minus IP, omega x plus IP. So this is the classical guy. So in the classic mechanics, you don't have to make operate or worry about the commutation relations between x and p. You can rewrite this as this if you wish. And then when you quantize this, this is already equal to something without the 0-point energy. So technically, that's a way to deal with these infinities without the normal ordering. But yeah, I'm not sure off the top of my head what other ways David Tong was referring to in the notes. Sorry. Okay. Okay. So I was just gonna real quick motivate the idea of where you get the classical or the physical momentum of our quantum field theory. And for that, I'm just gonna say something about symmetries, currents, and the symmetries of our Lagrangian in this case. So if you remember from your classical mechanics, typically when you have symmetries and continuous symmetries in particular, then you can use Noether's theorem to relate them to a conserved current. In this case, our Lagrangian, I'm just gonna write it like this, has a symmetry in that if I take x and I substitute it by x plus some quantity in any direction in time, in space, then the Lagrangian is still the same, the equations of motion are still the same. So there's an associated current with this transformation. There's also the fact that x can be rotated, or spatial x can be rotated, or the space-time can be combined with a Lorentz transformation. So each of these is what you would normally expect. The momentum to be the conserved quantity, the angular momentum, and this is the center of mass velocity of your system. So those things are conserved quantities. So via the Noether theorem, you can find that the conserved current, the momentum, is going to be given as an operator, or once you quantize the theory. So this is the physical momentum. That is the conserved charge of the x close to x plus a symmetry. This is going to be given by this quantity here. Okay, so again, I'm normally ordering the operator, and you see you get this numbering operator multiplied by the number p this time. So you have three different directions because obviously you have three different spatial directions. You can do the translation. So that means that these states that I talked about before, these p states defined as 2 omega p, a dagger acting on the vacuum, they have energy equal to the square root of p squared plus m squared, and they have momentum equal to p. So these states satisfy the relativistic invariance, energy momentum dispersion, the relativistic energy momentum dispersion. So this gives us peace in the sense that we were expecting a theory that was relativistic, even though we had these equal time commutation relations. And indeed, the states in our theory satisfy relativistic energy momentum dispersion relations. So that's great. So that was the quick mention of the momentum operator. But you can imagine that as before, we can have multiple racing operators acting on the vacuum, and those form new states. So an easy definition of a new state will be this 2 omega p1 square root of 2 omega p2, the racing operator ap1 and the racing operator ap2. So this new state has energy that is equal to omega p1 plus omega p2, and has, so this is the energy, and has momentum equal to p1 plus p2. So this pretty much looks like two particle states, right? The energy is the sum of the energies of the individual particles, and then the momenta are added linearly. And this is how we get the interpretation that these fields have particles as their quanta. Each of the excitations of the field will correspond to something that looks like a new particle on the field, that adds energy to the system, and then the momenta of the particle is added to the system too, in the way that you would naively expect this to happen. And the Hilbert space now, it's typically called the Fock space, where you have your ground state, you have your one particle states, you have two particle states, by combining the one particle states, but this is equivalent to having this notation that I had before. You have the 3 particle states, and so on and so forth. So now our Hilbert space, as you might imagine, is infinite dimensional, and it corresponds to different sectors where you have different number of particles. And since this is a free theory, then the different sectors do not really talk to each other. So you have some kind of conservation of particle number. Yeah. And something more that I wanted to add on top of that is that now the identity operator is going to be given by something like the ground state, the external product of the ground state, this integral that goes over all the possible single particle states, plus the integrals for the 2 particle states, P1, P2, and you get the idea. P1, P2, and then the external product P1, P2, P1, P2, and so on. That's going to be our identity operator. And I don't remember if I did, but as above, you have a number operator. Yeah, I think I did a number operator that dependent on momentum, but you can have a number operator that is independent of of the momentum, which is gonna be an integral over this other operator, where this was just AP dagger AP, right? Okay. So before we move into adding interactions, let me mention a different type of field, just so that you know how other fields will get quantized. So we have worked with scalar, but now we're going to introduce something called the complex scalar field. And the Lagrangian of this new complex scalar field is going to be psi. We wish psi is equal to field plus field 1 and field 2. But we're going to work with psi and psi dagger. So your Lagrangian has to be real. So you can only have terms that are complex conjugate of each other. And then you have, here you don't have the factors. And again, terms that are real. Real, and real. And in this case, the way that you will quantize the field is the raising and lowering operators don't have to be complex conjugate of each other, right? Something that we had before was square root of 2 omega p. So now we have a different operator here, where B and C do not have to depend on each other anymore. They're not related by complex conjugation. And now this guy is simply the complex conjugate of the guy before. Dagger. So you can perform a similar exercise with this new complex scalar field theory. But I'm gonna summarize or give you the answer as to the Hamiltonian of this new field theory is just going to be given by T3P to pi cube omega p of B dagger P plus C dagger P. So now we have two different numbering operators, in a sense, that are gonna be counting different species of particles, if you wish. There's also a symmetry in this case, so another new symmetry, where you can always change psi to E alpha psi. So this is a continuous symmetry. So Noether's theorem tells us that there's a charge. And the charge operator in this case is going to be given the difference between the number operators this time. So that should indicate us that in this theory, some of the particles have some positive charge, if you wish, and the other fields have negative charge. So the quanta of these fields, each of them will have opposite charges. And in this case, we will have that the numbers of one state minus the numbers of the other state, so what you might call NC minus NP, is going to be conserved. In the free theory, each of them individually are conserved since, as I said before, different sectors of the Fock space don't really interact with each other. So if you had 5 C particles, then there's going to be always 5. And then if you had 3 particles, there are always going to be 3 in the free theory. But once we add interactions, then different sectors of the Fock space will begin to be able to interact. But that cannot change the Noether theorem of the system, as long as the interactions still respect the symmetry. And the difference between these two numbers will not change. So you can keep creating particles as long as you create them in pairs, in a sense. So that's what it's called pair production. And it's a phenomenon that happens in quantum field theory. That's one of the additions that quantum field theory can explain, and quantum mechanics by its own cannot have this type of phenomenon. Okay. So any questions about this before I move on to the Schrödinger picture and the Heisenberg picture?
This is a boson behavior, but can we have a Fermionic behavior? We should change the commutation relation.
Yeah. So that's something that I don't think I will have time to go into much detail about, but you can have fields that have, in a sense, some kind of space-time index. So you can have fields. Let me not reuse the same. You can have fields that have some kind of space-time index, let's say alpha, that when you do one of these, I don't know, rotations in space, then you get some representation of the Lorentz group not operator, but matrix acting on the indices of the field. So different fields will mix. And depending on how they mix, then you can have them be have intrinsic momentum of 1/2, 1, etc. So if you have them, so far our fields transform trivially, so they are scalars. But then you have fermions, in particular spinors, so not fermions, let me call them spinors, which have, so the angular momentum or the spin of this is 0, spin of these guys is 1/2. You can have vectors where the spin is equal to 1. And as it works out, the spinors need to have anti-commutation relations for the Hamiltonian to be bounded from below or to be positive. So this is more of something that you will see in a more detailed quantum field theory course. But for now, I'm gonna stick with scalars. I'm not gonna deal with the subtleties of spinors, vectors, etc. But yes, with spinors, the commutation relations have to be different because the statistics needs to be different.
Thank you very much.
Okay. There's there's any more, if there's no more questions, then let me go to the Heisenberg versus the Schrödinger picture. So the Schrödinger picture in quantum mechanics is what you typically do, where you have your Schrödinger equation for your states. You have your Hamiltonian, and you solve this to get that your states evolve in time. Typically something, if this is an eigenstate of your Hamiltonian, then the time evolution is kind of trivial. And then if you want expectation values of, I don't know, the position, then this is going to be given by the time evolved operator sandwiching, or the time evolved state sandwiching the operator of position. And the operators themselves, you you interpret them as being fixed in time. They don't have any time evolution. In the Heisenberg picture, you assume now that your operators, Heisenberg operators, if you wish, have a time dependence given again by the Hamiltonian operator, that's given by this equation. Similarly, from this equation, you can derive some kind of Schrödinger equation of the operator that the time derivative is given by the commutator with the Hamiltonian. So notice the similarity to the Poisson bracket of classical mechanics. Where your fields had to evolve given by an equation that was very similar to this. Now, in this case, your states stay fixed. And for example, the expectation value would be given by a state that's just fixed, an operator that evolves in time, and a state that stays fixed. But since this is the definition of the time evolution, you should be able to see that this should give you the same answer as the Schrödinger picture. Where now this is the same as the time evolution of state psi. And similarly for the ket, the graph. So these two pictures are equivalent. It's just a matter of Are you evolving the operators or are you evolving the fields? In quantum field theory, we typically use something more similar to the Heisenberg picture in that our states are gonna be defined like the vacuum or the ground state. That's typically called the vacuum because it has 0 particles. The ground state is gonna be let fixed, or the number of particles in the initial state of your system is gonna stay fixed at some initial time, and then the final time of the particles at the final time are also like fixed in that final time. So given that, the dynamics of our field theory can also be given. So we have already solved the free theory, but we can solve it again with in this Schrodinger picture by applying, or this Heisenberg picture by applying this Heisenberg equation. Oh, it's not missing. Yes. And in this picture, you get the same answer as in the classical case with the Poisson bracket, where the time derivative of the field is equal to the momentum operator. Then the time derivative of the momentum operator is going to be given by this other piece of your Hamiltonian. Oh. And if you combine the equations together, so this equation and this equation, you find that your field has to satisfy this equation. But now this is at the operator level. These are operators in QFT. So the operators in QFT actually, at least in the free theory, actually satisfy the same equations of motion as in the free theory. Okay. So that means that we can solve for the equations of motion of the field and see how the field evolves in time. Something that it's useful to know is that if we make the operator of the raising and lowering operators evolve in time, meaning we apply this e to the ht on the right and minus e to the ht on the left, we just get, at least for the lowering operator, we get this omega pt. For the raising operator, I'm gonna get e to the I omega p t. So it's simple using this to see that our field depends on space and time in the following way. So now these are 4-dimensional Lorentz contractions, where I have that omega p is multiplying time and the spatial momentum is multiplying the space variable. Okay. So now we have our operators evolving in time. And in principle, you can take this definition and check what the commutation relations are now for the time evolving operators. And in the case of the free theory, it's going to be very simple because this time evolution is simple. These Hamiltonians are the free Hamiltonians. So it's not too complicated. Once we have an interacting theory, then this equation is not as simple as before. Sorry, here I miss the operator. So this equation is not as simple as it is here. And then the commutation relations as a function of time become complicated functions. Okay, so let's calculate some matrix elements of this time evolving operator. And the easiest matrix element is the vacuum expectation value of our field. So that would be just taking the ground state, which we identify with the vacuum since it has 0 particles, and sandwiching our time evolving operator. This case, we know that the field is proportional to A plus a dagger. So A is going to annihilate the vacuum on the right. A dagger is going to annihilate the vacuum on the left. So this is just 0. So in this case, this field has a 0 vacuum expectation value. Other fields, like the Higgs, have a non-zero depth or vacuum expectation value. And that's the origin of, for example, the Higgs mechanism. Again, it's a little bit of a complicated topic to summarize here, but this could be a good entry point for you to go look at more information for that. Okay, so let's try to compute something that's non-trivial. So now I'm just going to use x without the arrow to mean the 4-dimensional vector. So now I have the vacuum expectation value of 2 of these operators. And there are several ways that you can calculate this. You can follow the one from the notes. So just for fun, we can do a different one real quick here, where you insert the identity operator here, since the identity commutes with everyone. But I told you that the identity operator before was equal to this external product of the vacuum plus C3P 2 pi Q PP. I think there was factor of 2P here, plus so on. So the first term is going to be vacuum expectation of our field squared. We know that that is 0, so we don't have to worry about that one. The next term is going to be the interesting one, the D3P 2 pi cube pi of x p p pi of y 0. So you can play around if you wish with this derivation. One easy way to simplify things is to notice that in the same way that the time evolution could be extracted, also the position evolution, if you wish, can be extracted with use of the momentum operator. So you have something like this. And what this guy is the Hamiltonian and then the momentum, normal order, with normal ordering, as you might imagine. It's a 4-dimensional vector, but of operators, where you have the Hamiltonian and then the momentum operator. And this allows you to translate the field back to the origin. If you use that simplification, you will get something of that is independent of x, and so you get this integral to p. the nice thing is that these operators acting on our states, they have a simple have a simple representation because P in this case is just the number, the four momentum of numbers. We have omega P and the vector P, no longer operators. So these are become numbers such that this is equal to minus IP x minus y, and the matrix element of the operator at zero with the momentum, with the state P squared. So coming from each of the two contributions. And each of them is conjugate of the other, so that's why you get the absolute value. You can check out by yourselves that because this is going to be given by something plus a dagger, this can be checked that this is equal to 1. So our first non-zero vacuum expectation value of our fields in the free theory is going to be given by this integral here. Okay. And before we finish for today, I'm going to define another conventional operator of operators, if you wish, which is called time ordering. And with the time ordering operator, represented with this T, it means, or you don't even have to use it as a vacuum expectation value. The time ordering of an operator, or of a set of operators, means that if the time component of x is bigger than the time component of y, then this operator is simply the thing that I wrote. But if the time component of y is bigger than the time component of x, is greater than, then you have the fields in the opposite way, where you don't have to worry about the fact that they might not commute, or that the that the ladder operators within these two fields will have some commutation relations. The time order operator says, don't worry about that. This is the definition of this operator here. This is something that we will do in the next session, is to calculate the time order operator, the vacuum expectation value of the time order operator of the two fields. Okay. And spoiler alert, this is called the Feynman propagator. Okay. So I'm gonna break here for today. If you have any questions for all the stuff that we have talked about here already, it's a good time. Tomorrow, basically what we will cover is the time evolution of the fields that of the time evolution of states that are asymptotic states. So something that looks like a scattering state, and something called the Dyson series that tells you how to calculate basically these scattering processes. And from there, we're going to show that to calculate those things, you can draw pretty pictures called Feynman diagrams that have to do with the interactions in the theory, and how to go from the Lagrangian that gives the interactions to the pretty pictures that allows you to calculate the transitions. But that's for tomorrow. Today, if you have any questions, please go ahead. Also drop them in the chat.
Hi, Felipe.
Hello.
Thanks for the lecture first. And when you are talking about the vacuum expectation value, why the vacuum expectation value is 0? Why?
So in this case, this is what the calculation comes out. So if you remember, the free field is going to be proportional to a lowering operator plus a raising operator. And the
Yes.
lowering operator hitting the vacuum, that's equal to 0. So that first term, it goes to 0 already. Then the raising operator hitting this other vacuum, that is going to be equal to 0. Or in other words, if you think what happens when this raising operator hits the vacuum, then you create a one particle state. Then, as I said before, the different sections of the Fock space don't talk with each other in the free theory. So far, this is the free state, the free theory. So the one particle state contracted with the vacuum, that matrix element is going to be 0 because they are orthogonal states. If you have an interacting theory like the standard model, when you have the Higgs and other stuff, then this no longer has to be true. Especially if you have a potential that's very different from the potential that we have here.
Okay. I have another question.
Yep.
We could use a kind of Schrödinger picture in quantum field theory too.
Yeah, in principle, there's nothing preventing us from doing that. And in fact, that's what I did with the free theory at first, where I solved for the Hamiltonian. So I have the Hamiltonian and I had the spectrum of my Hamiltonian, and then I could just take states that are linear combinations of any of the states in the Fock space and evolve them in time, given that I know the energies. The complication is that once you have interactions, then solving for the spectrum becomes basically impossible. So you have to do other stuff in order to access information from the theory.
Okay, thank you.
Are there any other questions? Okay. Well, we're gonna be back here tomorrow, same time, for the final part of this lecture series. You wanna say something else, Raul, before we go?
I was gonna say, why don't we all give a big thanks to Felipe for a nice talk. You can use your applause emojis, or you can turn on your camera, or you can just put it in the chat. Either one counts. All right. With that, thanks again, Felipe, and we'll see you guys tomorrow. Ciao, ciao.
Bye, guys.